Well, hello and welcome again to our journey into algebra and number theory. And in this next series of videos, we're going to have a look at congruences and residue classes. So in previous sections, we looked globally at the integers as an example of an infinite ring. The notion of congruence, which was developed by Gauss, enables us to parcel up the integers into blocks called congruence classes. And turned out to be, as many of Gauss's ideas were, a particularly brilliant idea to do this. So these blocks we're going to chop up the integers into are called congruence classes. This will give us useful examples, in fact, of finite rings, and enable us to introduce the notion also of a finite field. In addition, many important questions about the integers as a whole can be answered by looking at congruence classes. So we know, for example, that I can take any integer and I can divide it by 5, and we only get 5 possible remainders, 0, 1, 2, 3 or 4. And I'm going to then partition the integers up into, firstly, all the numbers that leave a remainder of 0 when divided by 5, that is the multiples of 5 that were previously written as 5z. I'm going to write that for the moment as 0 with a little bar under it. So these are the ones that leave a remainder of 0. So this object here is actually an infinite set of numbers. I'm going to take all the numbers that leave a remainder of 1 when you divide by 5, so 1, 6, 11. And I'm going to write that as 1 with a bar under it. All the numbers that leave a remainder of 2, 3 and 4. And so every integer is mentioned in the union of these 5 sets exactly once. And so this represents what we call a partition of the integers. A partition means that every integer gets a mention somewhere in here, and no integer belongs to more than one set. So two elements are said to be congruent modulo 5 if they lie in the same set. So I like to think of this as when I'm doing mod arithmetic, I'm wearing special glasses where, for example, if I'm working mod 5, I've got my mod 5 glasses on, then if I'm looking at the number 1 or 6 or -9 or 11, then they all look exactly the same and all I really see is just 1. That is, we can identify every number in this set with just the number 1. And normally, when we do this, we're not going to put the underlines. I've just done them here initially, but we normally drop the underline very quickly. So, here's our little definition to try and make this a bit more precise. So if we take two integers a and b, and I take an m which is a positive integer, and m is going to be our so-called modulus, then we say that a is congruent to b, which is the way we're going to read this. A is congruent to b mod m, means that m is a factor of a minus b, which is the same as saying a and b leave the same remainder when you divide by m. And so if you subtract the two numbers and divide by m, there'll be no remainder. So m is a factor of a minus b. So that is, two numbers are congruent if they leave the same remainder when divided by m. So again, if I've got my mod 5 glasses on, when I see 12, then I really see 2. These numbers are identical, they're congruent as long as I've got my mod 5 glasses on, reading at mod 5. Similarly, 17 is congruent to 7 mod 10. Both of these leave a remainder of 7 when you divide by 10. And 13 is congruent to -9 mod 13, because if I divide either of these numbers by 13, the remainder is 4. So they have the same remainder, so they're congruent. One way of getting from one to the other is just to subtract off. So I could take 17 minus 13 is 4, subtract off 13 again gives me -9. Now every integer is congruent modulo m to exactly one of these numbers, 0, 1, 2 up to m minus 1. This set of numbers is called the least set of residues or least remainders modulo m, and we're going to denote it by z sub m. You may have already seen this in other courses in number theory. So observe then that A is congruent to B mod M. Another way of writing that is, we said that A minus B is divisible by M. So that says A minus B is Km for some integer K, and that's the same as saying A is B plus M times K for some integer K. Now I've listed here as a theorem, but I'll leave you to prove the results. You just simply use this definition or use this result all the time. It comes out fairly easily. Or the definition, whichever you prefer. So this is just a list of some of the properties. So if I've got two different moduli, m and n, positive integers, and a, b, c, d, any integers, then the following is true. A is always congruent to itself, obviously, because a minus a is 0, which is divisible by m. If a is congruent to b mod m, then b is congruent to a. So this is a symmetric relation. If a is congruent to b mod m and b is congruent to c mod m, then a is congruent to c mod m. So this relation is transitive. If a and b are the same mod m and c and d are the same mod m, then you can add the two equations and it's still true, or you can multiply the two equations and the result is still true. And if a is congruent to b mod m times n, then a is congruent to b mod m and a is congruent to b mod n. That takes a little bit more proof, and I'll leave you to have a look at that one yourself. Just to see a little bit of why the power of these congruences, and why we'll see a lot more of the power of it shortly, but to see why they're so useful, here's a very simple problem. I want to take this number 13 to the 2000 plus 1, and I want to show that if you divide this by 3, it's not divisible by 3. There's a non-zero remainder, and in fact we can get what the remainder is. This number is far too large to calculate by hand, so we don't want to do that. So we're going to use congruence. So we're going to take this number here, and I'm going to put on my mod 3 glasses. So I'm going to read this number modulo 3, and this of course is 12 plus 1. So modulo 3, this is just 1. And 1 to the 2000, of course, is just 1, and 1 plus 1 is 2, and that is not divisible by 3. So this is 2, this is not 0 mod 3, and that tells me that this number is not divisible by 3. On the other hand, if I want to find what's the remainder when I divide 2 to the 1001 by 5, for example, well, again, you use some mod arithmetic here. I'm going to take out one of the 2's out of here, so I get 2 times 2 to the 1000. I can square that 2 and write that 2 to the 1000 as 4 to the 500. Now I put my mod 5 glasses on, and I can replace 5 with minus 1, modulo 5, and minus 1 to the 500 is 1, and that gives me 2 mod 5. So that tells me this number has a remainder of 2 when you divide it by 5. Another little exercise here is to prove this number is never a square. This one you might do in various ways. I'll leave you to have a think about that one. You can do it by mod arithmetic. You can also do it without mod arithmetic, in fact, because if you think about it, whenever you raise 5 to any power, the number you get will end in 5. And then if you add 2 to that, the number you get will end in 7. And you need to convince yourself that no square ever ends in 7, which you can do by mod arithmetic again. Slightly more sophisticated example is applications to Diaphantine equations, and this is where it really gets quite pretty. So suppose we have a Diaphantine equation, so here's one here, x squared plus 1 is 2y to the 4th. Now this one is a very famous equation. It's called Congruent's equation, and it has been solved. And we know what the solutions of this are. There's only 2 of them. There's, in fact, the x is 239 and y is 13. X is 239, y is 13. So there are the other solutions, and of course you can have plus or minus one of those, and the other solutions are plus or minus 1. In fact, of course, 1 plus 1 gives you 2. Amazingly, these are the only integer solutions it has, but the proof of that is incredibly difficult. I'll leave you to look it up if you're interested in this. It's called Lundgren's equation. Starts off with double L-U-G-R-E-N, Lundgren's equation. However, if we read this, if I put my mod 5 glasses on and read this equation mod 5, that is this one here, then we see that if I look at this solution, look at this equation, read it mod 5, well then I can write this one as 4. This really says 4 squared plus 1, and 13 is the same as 3. And if you calculate these, this is 17. And if you calculate this mod 5, you get the same answer both sides, so it is still true. In other words, if you've got a true statement and you read it modulo m, and then the result you get must still be true modulo m. Now, taking the contrapositive of that, if we can show that a Diaphantine equation cannot be solved in Zm for some suitable choice of m, then it can't have any integer solutions. Now, of course, the converse is false, but this way round is still very useful. For example, I'll take this equation, x squared minus 10y squared is 3. I want to prove that this cannot be true in the integers. Now, of course, there are other ways of doing this, but using mod arithmetic is particularly nice. If I put my mod 5 glasses on, then this is 0. And so I just get x squared is 3 modulo 5. But now if I look at the squares in Z5, so 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 4, 5, and that's it, because 5 gets you back to 0 again. So the only squares in Z5 are 0, 1 or 4, and so x squared is 3 mod 5 can't happen. And if this equation has no solutions mod 5, it's got no solutions at all in the integers. That's a very powerful tool there. We can also use this to develop divisibility tests. So congruences, mod 10, 100, etc. can be used to give tests for deciding whether given numbers are divisible by 3, 9, 7, 11 and 13 and so on. You probably perhaps know this from primary school, that an integer n is divisible by 3 or 9 if and only if the sum of its digits is divisible by 3 or 9. And the proof of that's fairly simple. So you write n in decimal form. So for example, if I had n to be 396, so that's 396. I'm just writing the digits down in decimal form. Now if I unpack this decimal form, then that means it's 10 to the n times a sub n, 10 to the n minus 1 times a sub n minus 1, plus all the way down to a sub 0. And so I can say if 3 is a factor of n, then that means n is 0 mod 3. And I can write my n in, I should not have used n here, that's very naughty. I will use k here. So I'll say 3 divides k, and that'll be k there. I can't use the same symbol with two different meanings. So suppose k, an integer k, is divisible by if and only if the sum of its digits is. That's better. So I'm going to write k in this form. Then 3 is a factor of k. That means k is congruent to 0 mod 3. And I'm simply writing k now in this decimal form. And that means that's got to be 0 mod 3. But then all of these powers of 10, 100, 1000 and so on, all the way here, they're all congruent to 1 modulo 3. And so this just collapses down to the sum of the digits is 0 mod 3. And that simply says the sum of the digits of k is divisible by 3. Well, you can do a similar test for divisibility by 11. What happens there, of course, as you probably know, you get the first minus the second plus the third minus and so on, because the powers of 10 alternate between minus 1 and plus 1 modulo 11. For 7 and 13, I'll leave you to develop your own tests. You have to work mod 1000 because 1000 is congruent to minus 1 modulo 7 or 13. So for example, if I take 10,094, then I can write that as 10 times 10 cubed plus 94. 10 cubed is congruent to minus 1 modulo 7. So this becomes minus 10 plus that, and minus 10 plus that's 84, and 84 is divisible by 7, so that's 0 mod 7, and that tells me 7 is a factor of this number. We'll have a look in the next video at some of the properties of this Zm, in particular its addition and multiplication tables.